Okay, friends, now we're on to the last problem, the famous conical tank problem, or conical pile problem. In fact, if you were to look up it in any calculus book that's ever been published, probably dating back to the 1700s when the first calculus book would have been published by L'Hopital, there's probably a conical tank problem or a conical pile problem in there. Now, I realize that there aren't too many tanks that are shaped like cones, but this just involves some good math and some good modeling. So we're going to knock this out, and hopefully you can see that a conical tank problem really isn't as hard as students often make it out to be. So it says water is pouring into a conical tank. You saw that animation on the video. And there are different things that are changing, right? And you probably identified that the depth of the water is changing, the volume of the water in the tank is changing, the diameter of the water is changing, lots of things that are changing. And so it says here that the water is coming into the cone at a rate of 4 cubic feet per minute. And that says the container is in the shape of a cone with a base diameter of 6 and a depth of 8. So the total height of this cone is 8. The base diameter is 6, which means that the base radius is 3. Okay? So now what I'm going to do here is I'm going to sort of put the water level in here, right? And then I'm going to say, all right, well, I'm going to identify, because now we know that we draw a picture and identify some variables. There's two different radiuses happening here. There's the radius of the cone itself, but then there's the radius of the water, okay? So the radius of the water, if you look down on, the water would be in a circle, right, just getting bigger as it goes up. The radius of the water I'm going to call R, and the height of the water, or the depth of the water, I'm going to call H, okay? So I've got a picture here, and I've identified some variables, and I've labeled some things. Now, you got to think about who's constant here. What's constant? What's not changing? The 3 is not changing, and the 8 is not changing. The size of the cone, the tank, the container is not changing. But the water level in it is definitely changing. The volume of the water in it is changing, the height of the water is changing, and the R is changing. Okay? Now, what do we know? Okay? So what do we know here? What do we know in this problem? They're telling us that the water is pouring into a cone-shaped container at a rate of 4 cubic feet per minute. 4 cubic feet per minute. What kind of rate does that sound like? So, well, it sounds like a volume. So I know that dV dt is equal to 4. It's a constant 4. Okay? The volume is changing at a rate of constant 4 cubic feet per minute. Okay? What do I want to know? What do I want to know? It says, find the rate at which the water level is rising when it's 3 feet deep. Find the rate the water level is rising when it's 3 feet deep. So what rate is that, would you think? What rate would we describe the rate of change of water level? Right, dH dt. So I want dH dt, and when do I want it? When h equals, I forget already, 3. Okay? So I know dV dt is 4. I want dH dt when h equals 3. Okay, now the next step is to find some sort of relationship between V and H. Okay? Well, if you think about this, water inside that cone tank is always going to take on the shape of a cone. So the volume of that water is just going to be the volume of a cone, which, in case you didn't know, was 1/3 pi r squared h. Okay, that's the volume of a cone. Okay? Oh no. What's in this equation that is nowhere to be found in our given information right now? R. We don't have anything about R, right? Well, let's see if we can figure something out here. And this, honestly, is why this problem is in every calculus book that's ever been published, because there's some good math involved. If you think about this scenario here, okay, let's say that that's a cutaway of the cone, the whole cone, so that this is 3 and this is 8. Well, the water level is here, right? And so let's call that H and that R. Okay, that's just half of it, right? But do you see a relationship between H and R? There's similar triangles here, okay? There are similar triangles here. So it looks to me like this triangle right here and the big triangle, okay, are similar. Make sure you understand that that 8 goes for the whole dude, okay? So it looks to me like what? R over 3 equals H over 8. That's one way of writing the proportionality of that. So now I have a relationship here between R and H that I can use over here. Okay, so let's get R in terms of H. Well, it looks to me like R is 3/8 times H. Okay, R is 3/8 times H. So now I'm going to take this and I'm going to plug it in over here. Okay, so what did that do for me? That gave me V all in terms of H, which makes this part easier. I don't have to deal with anything with R in it. Okay, so now I'm going to clean this up slightly. 3 squared is 9, 8 squared is 64. And then I'm going to just write that as H cubed. H squared times H. Okay? And if we really want to, we'll go ahead and say that's 9 pi over, 3 times 64. 3 times 60 is 180. 3 times 12 is, or 3 times 4 is 12. So 180 plus 12 is 192. Okay, so let's stop for a second before we do any more before we even do any calculus. What are you looking at right here? What is this equation telling you? This equation right here is telling you what the volume of the water in the tank is for any height of the water. Whatever the height of the water is, that's the volume of the water. Okay? So now we've got V in terms of H, and now our next step, we got a relationship between V and H. Our next step is to differentiate that equation with respect to T. Okay? So dV dt does equal dV dH times dH dt. I'm running out of ink here. I'm going to have to run to the store and get some new markers. Okay? So here we go. dV dt is, well, let's bring the 3 down, so that's going to be 27 pi over 192. Now, friends, that's just, this is all just a big constant here. Just leave it as a constant. H squared. So I brought the 3 times 9 and made 27, okay? So this piece right here is dV dH. And now we're going to multiply by dH dt, okay? Now, we can substitute then solve, or solve then substitute. It's up to you. I'm running out of room, so I'm going to have to maybe pause this. And no, I'll just erase. No. Yeah. I'm going to pause this and erase this part right here, and then just keep going. You guys just keep going on your paper. I want these similar triangles here because I'm probably going to go back and refer to them again. So give me 1 sec. Okay. So we're back here. I took what was down here and I just put it at the top, and then I took the no's and the once and put them over here just so I could refer back to them if I needed to. Okay, so I know the dV dt is 4 from the given information. I want dH dt. When do I want it? When h equals 3, right? So in this case, I'm going to go ahead and I'm going to solve for dH dt and then substitute in the stuff that I know. just because we've done it a couple different ways, and you have the choice on how you want to do that. So I'm going to say that dH dt is going to be dV dt divided by 27 pi over 192 h squared. Now that looks like a hot mess, right? I mean, that's just a huge, yucky mess. But we're going to do all this calculation on a calculator here, okay? We're not going to try to do all this arithmetic by hand. That's foolish, okay? So I want dH dt now when h equals 3. And if you notice here, this whole side has stuff in it that I know, right? So I can substitute in dV dt, which is 4, and I can go ahead and put 27 pi over 192, and then h squared. Well, I know I want dH dt when h equals 3, so that's where I'm going to put my 3 squared. Okay? So let's go ahead and compute this. I'm going to pause this so you don't have to watch me type on a calculator. Okay, so Big Red here told me 1.006. Okay, so you might want to double check me on that. It's dark in here, so I might have typed something incorrectly. So dH dt when h equals 3 was 1.006. What are the units on that? Okay, well, what are the units on h? The units on h are feet, right? And what are the units on t? Seconds, I believe. So when the depth of the water is 3 feet, at that instant, if we were to hit a radar gun on it, the depth of the water would be rising at 1.006 feet per second. Okay? Does that make sense? So that's the conical tank problem. Now, in another video, we're gonna dig deeper into this conical tank problem because I really would like to go over here and have some discussions with you about that relationship between R and H and how are those things changing with respect to each other. But that'll be another time. So there you go. There's 4 examples of related rates problems. Some 4 classic ones. You have a conical tank. You have a Pythagorean theorem triangle one. That was the kite problem. And then you had the circle problem. And then you also had the triangle problem, the kite problem with the angle. Yeah. Take care.